Okay, so in the next few lectures, I'm going to really talk more about concepts and ideas rather than doing mathematical derivations. And so what I want to talk about now is I want to talk about how contact interactions go very far to helping us explain how matter is put together, how matter works. And so the basic principles of atomic interaction have to be understood, and we understand them through four basic ideas. So four principles. Principle one is that matter is composed of atoms. This may seem very basic to us. We live in a world where we understand that atoms are the building blocks of all materials, at least baryonic matter, the stuff that we touch and see and exerts gravity and things like that. But in 1904 and before, there was no real theory that got it right. The best possible theory in 1904 was from J.J. Thomson, a British chemist and physicist. And J.J. Thomson, I think he was also Lord Kelvin. He proposed what was known as the plum pudding model. Kind of a weird British name. But his idea was that matter was made up of a soup of electrons, or a pudding of electrons, a dessert, surrounded by some positive material. Didn't really know what it was. They knew that electrons existed. Electrons were discovered. But they didn't know how electrons in this positive neutral matter, because if this was, say, for example, 4 electrons, this would have been plus 4 positive something. But of course this is wrong. This is not the way that matter was put together. And so a very bright person from New Zealand, actually, named Rutherford, Ernst Rutherford, he went to Cambridge and started to work on understanding how matter was put together. And what he did was he said, okay, well, what I'd like to do is I'd like to take a thin foil of gold, let's say, and I'm going to take a little accelerator, like your capacitor that you had in your experiment, but set in a different way, and or in your homework, and he was going to shoot alpha particles at a very high rate of speed towards this very thin gold film. And what he found was that this very thin film, he put a collector of all of the, so he could capture all of his alpha particles. This is an alpha particle detector. And he blasted his alpha particles towards the detector through the film, and he expected to see, maybe some divergence. These are positive charged objects. And if there was some soup of things, he was expecting to be able to determine how the distribution of these things looked. And when he counted the number of alpha particles here, he expected to find the same number of alpha particles here. He wanted a big equal sign. He needed those two to be equal. Well, they weren't. There were lost alpha particles. So he ingeniously set up another detector back here. And what he found was that some of these alpha particles bounced back. And in the plum pudding model, it shouldn't have happened. They should have been deflected a little bit, but they should never have run into a brick wall and bounced. And the brick wall that he ran into was, in fact, the nucleus. And so he proposed that those atoms, those atomic materials, were actually more of a contained positive object, the nucleus, that was surrounded by some set of electrons that could be composed as a object, a building block. And when he shot his alpha particles, sometimes they hit the nucleus, which was positively charged, and they bounced right back. Because the density of the nucleus was large. These are gold, just like some of the experiments that you explored in your homework. The bounce, or the deflection of those objects led him to come up with an idea that atoms were actually more of a condensed object. Okay, so that's number one, and a little bit of history. Number two is that atoms attract when close together. But not too much. We don't want our atoms to slam together and be stuck forever right on top of each other. We don't want the nuclei to form another nuclei. That would be fission. We don't want that to happen all the time, because then there wouldn't be anything except a big lump of protons and neutrons. And so there's a finite distance that they have to be from each other. And those are what set the bonds and the bond lengths. So there's a slight attraction between my atoms at some distances, but when I try and push them further and further together with a force, they actually repel. So now, if I try and go too hard, these atoms are going to push back. And there are fundamental physical laws that were discovered during the era of the 1920s that helped us understand why that would happen. So, the third principle is that atoms repel if they get too close. And so there's this balancing act between wanting to be together. They want to condense to form an object, a molecule. But if we try and push them too close together, they start to push each other away. They can't occupy the same space. And the fourth idea is that atoms always move unless they are at absolute zero. T equals 0 Kelvin. Now, no one on Earth until the late 90s had ever seen an atom at absolute zero. However, in 2001, a Nobel was given to two groups, one at UC Boulder and one at MIT, for finding materials, essentially sodium atoms, that can be condensed into what's called a Bose-Einstein condensate. And so that was a material that reached absolute zero in the lab. The coldest thing on the planet.